I want to talk about Kurzweil's idea of the singularity at a couple of levels. First, I want to address it from the point of view of just plausibility. And secondly, accepting that he's right, let me talk a little bit about what some implications might be. So I have read Kurzweil here and there, of course, over time, but I had not sat down with the book until after Roger put this panel together. And I thought, well, all right, I will sit down and begin reading. And I was telling Keith on our walk over, I didn't get nearly as far as I had planned because I had to keep putting the book down to walk around the room and or to explain to my dog why he was so wrong and how he was so mistaken about this or that or the other thing. And so I have put it aside for a day so that I would be calm-ish today. But I want to focus on one of the particular claims on which he builds his estimation that we will reach the singularity by 2045, give or take. He builds this in large part on the argument that progress of a certain kind happens exponentially. And he spends a lot of the first 50 or 60 pages of the book talking about this, and he refers back to it a lot. So what is this getting at? Well, Moore's law, which Bill has already referred to, says that in its most basic form, that the number of transistors that we can put on a computer chip roughly doubles probably every 18 months. What does that mean? That means a lot of things. How much we can store in memory roughly doubles as well. Computing power, in some sense, doubles about that quickly. In many, many, many kinds of measures, computing power has indeed sort of doubled every 1 to 2 years. And so if you graph the progress of computer power, it sort of looks like that on a graph. Or if you graph on a log-log graph, which he does, it is a nice straight line. Fine. He wants to compare this to biological evolution. And here I'm afraid he goes really quite astray. He makes a number of assertions about the way evolution has worked that just don't quite hold true. And I know because I trotted down the hall to ask one of my biology colleagues, does this sound right to you? Does this sound right to you? Seemingly not. But I think the argument about biological evolution also increasing exponentially is a side point to his argument. Right? It's sort of the idea that humanity and technology will somehow merge doesn't really require that biological evolution has accelerated in this exponential way. I think it sort of adds to this flavor that everything really happens faster and faster, which is true in the technology point, not really true in the biological point. So his biological points are that complexity and order have increased and increased at an accelerating rate. And in fact, it's just not true. Most of the biomass in the world is actually single-cell organisms. There are increasingly complex organisms, but we don't make up more and more of the biomass, which is one way to sort of measure, right? The percentage of organic stuff that is mammalian, for instance, is actually very small. There are lots and lots of bacteria, and not so many mammals, for instance. It's not clear what he means by the order increasing. So I don't want to give this too short shrift. I just want to say, well, with biology, I don't think his arguments really hold together. Maybe if we go back and redefine some terms, we can salvage some of it. But let me turn to the computational side. He relies on the assertion that computational power has increased exponentially, and he's right. And therefore, he says, that will continue to happen, which is probably true. He points out that we're approaching the physical limit of current silicon-based, transistor-based computing technology. At a certain point, the transistors get so small that you just can't shrink them anymore because single atoms are now doing the motion and you can't have a smaller piece, right? Or single electrons are flowing through a channel and you can't get smaller. So there is a physical limit. And he says, perhaps correctly, there's always a paradigm shift. Right? We hit a limit and then we figure out a new way. He proposes three-dimensional computing components. Maybe that's the right way to go. Others might propose quantum computing. That's another possibility. So, okay, let's accept that there might well be a paradigm shift, and that the exponential increase in computing power will continue. What he concludes from that is that then essentially computational abilities will be unlimited. We can do anything, right? He calculates how much computation he thinks the human brain can do. And he quotes a number of people who've tried to compute it in a number of ways, and they all seem to agree within a couple of orders of magnitude. I think we would have to say that these are very primitive calculations. Right? They're based on very simple assumptions. But even if he's off by a factor of 1,000,000, it doesn't destroy his argument. Really. It only pushes the singularity back 30 years or something. So, okay, we'll let it go. But is it true that if computing power grows exponentially, that therefore eventually we can solve any problem? No. There are uncomputable problems. Okay, let's restrict ourselves to the computable problems. Does it mean that pretty soon we'll be able to solve every computable problem really fast? No, it doesn't. The one area of computer science that he sort of doesn't really talk about is an area called theory of computation that I teach. And one thing that we talk about is that there are certain problems whose complexity to solve grow exponentially. So one example, the sort of standard example, is called the traveling salesperson problem. Here's the problem. I give you a bunch of cities, and I tell you the distances between every pair, and I ask you, what's the shortest route you can take that visits all the cities once and comes back to the starting point? That's an easy problem to state. Right? It's a hard problem to solve. It turns out the best solution we know of is to actually compute all the possible paths through all the cities. So if you have 3 cities, it's easy. It's a triangle. 4 cities, you could go that way, or you could go diagonally first. There are only really a couple of possibilities. But it turns out, as the number of cities grows, the number of possibilities goes up exponentially. So, what's the implication of that? Well, if computational power goes up exponentially, but the complexity of solving the problem goes up exponentially as well, the two things are just sort of keeping pace with each other. Right? It's our intuition that if next year I can buy a computer that's twice as powerful as the computer I have now, then all the things I do with the computer should run twice as fast. But it's not so. If right now I could solve the traveling salesperson problem for, say, 100 cities, and next year I buy a computer that's twice as fast, then next year I can solve it for 101 cities. And in 10 years, when the computers are 1,000 times faster, 110 cities. Okay, why does that matter? Well, the point I'm trying to make is that exponentially increasing computing power might buy you much faster processing, but it might not. It depends on the problem that you're solving. And if you're solving a problem where larger and larger instances are exponentially harder to solve, you actually just get sort of constant increase. Well, what if the kinds of problems that our brains do have that kind of flavor, have that kind of exponential growth flavor? Then computers will indeed gradually approach sort of the computational power of the brain, but at a much, much slower, not an exponential rate, but rather a linear rate. That pushes the singularity off very far into the future, if it's going to happen at all. So, on the one hand, I don't want to dismiss Kurzweil's ideas. The idea that we will have neural implants. Clearly this is happening. Right? The idea that we would choose to augment our cognitive abilities with machines. We already do. We don't implant them yet. But we carry around our calendars and our address books and things on electronic devices. So I don't question the basic idea he's making. I think his estimate of the time is far off. And I find it a little hard to forgive the glibness with which he sort of skates over a number of what are fairly complicated issues, I think. But let me put aside the plausibility and the sort of time frame argument. Is it true that it's sort of inevitable that computers and humanity will merge in some way? Probably, depending on what you mean by merge. We already have people with cochlear implants. That doesn't seem to be a bad thing. There are people working on developing artificial retinas for blind folks. That doesn't seem to be a bad thing either. I showed a video, or attempted to show a video in my cognitive science class last Thursday of a young man who had no hand and had been fitted with a robotic hand that actually interfaced in some way with his neural system, and it wasn't entirely clear how that worked. And it was fairly crude, but he could open and close it. And there were sensors so that he could tell whether his fingertips were touching something. So the technology is coming. What does that mean? That's a great question. I'm very tempted to say at this point, oh, I'm a computer scientist and I don't know, sort of step out of the room. But I won't. What does it mean? At the very least, it means we're going to have to rethink, as Bill made the point very well, we have to redefine some of our terms. We'll have to rethink what it is to be human and what's distinctive about humanity. That's not new. We've done that a number of times, right? One of the things I like about the current first-year seminar readings is that I think one way to look at a number of them is to think about ways that science has forced us to rethink what humanity means already. Right? Genesis has us at the center of creation. And then it turns out we're not, certainly not geographically. What does that mean for what it is to be human? Well, okay, so we're not the center of creation, but we're still perhaps created, but just not at the center. And then Darwin, creation, okay, evolution leads to us. And I think a biologist would say, well, evolution leads many places, one of them being us, but it's not necessarily a directed process. Artificial intelligence challenges us, right? Is what's central about humankind our ability to think logically? Well, perhaps not. Machines can think, in some sense, logically already. Machines play checkers, for instance. Machines play checkers better than people. Chess is not a solved problem in the way that checkers is, but it's very difficult for a human to beat a computer. But we keep readjusting what it is that's special about humanity, right? This has never defeated us yet. There's never been a scientific discovery that has so crushed us that we can't decide that there's still something distinctive and important and valuable about what it is to be human. Whatever it is that happens, and I question the idea of the singularity as Kurzweil imagines it, but whatever happens as we start to incorporate technology, I have no doubt that we will come to a new understanding of what it is to be human and what is special about that.